Welcome back. I am Deobrato Goswami and today we are talking about ethers. Before the break, I had asked you, is the preparation of ethers using alcohols a unimolecular or a bimolecular reaction? Well, let me take you back to the reaction. If you remember, two molecules of alcohol combine and lose a molecule of water to form an ether. It is a bimolecular reaction. Now that you know the reaction is bimolecular, let's study the mechanism of the reaction. Preparation of ethers by dehydration takes place by SN2 reaction. Let us now move on to a step-by-step breakdown of the reaction. In the first step, protonated alcohol is formed. In the second step, an alcohol molecule attacks the protonated alcohol. Then, the ether is formed. This method is useful, but it has its limitations. What are those? Let's see. First, we can use this method only when a primary alcohol is used as the reactant. In case of a secondary and tertiary alcohol, dehydration gives the corresponding alkenes, not ethers. The other major limitation is that this reaction works only for symmetrical ethers. However, when different alcohols are used as reactants, a mixture of ethers is obtained. Well, that's how we prepare ethers. I know there must be many questions bubbling in your minds. In fact, we have a caller with just such a query.
Hello sir, I am Abhinav Saingar. I want to ask you a question. You have told us all about the preparation of symmetrical ethers. But how do I prepare an unsymmetrical ether?
That's a nice question. Well, unsymmetrical ethers can be prepared by using a reaction called Williamson synthesis. That is what we are going to look at now. Williamson synthesis is a very important laboratory method for the preparation of both symmetrical as well as unsymmetrical ethers. The process involves an alkyl halide which, when treated with sodium alkoxide, leads to the formation of an ether and a sodium halide. In this method, we begin by preparing sodium alkoxide. How do we do that? Well, sodium alkoxide is prepared by the reaction of sodium with alcohol. It's clear that the Williamson method involves a substitution reaction. But can you predict whether Williamson synthesis is electrophilic or nucleophilic? Think about it. In fact, let's take another look at the reaction. As you can see, the halide ion in an alkyl halide is substituted by an alkoxide ion. This makes it a nucleophilic substitution. Let's understand this by studying the mechanism of this reaction. Initially, the nucleophile, which is the alkoxide ion in this case, attacks the alkyl halide Rx. Then, the halide ion, denoted by X-, leaves as the leaving group, forming sodium halide. The ether is also formed side by side. For better results, however, the alkyl halide should be primary and the alkoxide should be tertiary. If you take a look at this example, the reaction of sodium tertiary butoxide with bromomethane gives the ether 2-methoxy 2-methyl propane and sodium bromide. Now, what do you think happens to the product in Williamson synthesis when the alkyl halide is tertiary and alkoxide is primary? Think. Well, when a tertiary alkyl halide reacts with a primary alkoxide, the only product formed is an alkene. A good example for this is the reaction of sodium methoxide and tertiary butyl bromide, which exclusively forms 2-methylpropene. This reaction does not form ether. The reason for different products being formed is that alkoxides are not just nucleophiles but are also strong bases. Let's take a look at our reaction once again. As you can see, the attack on the carbon attached to the leaving group is difficult due to steric hindrance. So, alkoxide cannot act as nucleophile here. What happens instead is that the alkoxide ion accepts a proton, leading to an elimination reaction. The alkoxide ion acts as a base. The result of the reaction is an alkene. Secondary alkyl halides also form alkenes as the major product due to elimination. And interestingly, alkyl aryl ethers and phenolic ethers can also be prepared using Williamson synthesis. Here is how. We begin by preparing sodium phenoxide using phenol and sodium hydroxide. Sodium phenoxide then reacts with an alkyl halide to form an alkyl aryl ether. For example, methoxybenzene is prepared using sodium phenoxide and bromomethane. Now that we know about how ethers are prepared, let us talk about their chemical properties. How do ethers react with hydrogen halides? This reaction of ethers shows the cleavage of carbon-oxygen bond. How? Let us see. Firstly, dialkyl ethers react with hydrogen halides to give 2 molecules of alkyl halides. But remember that the reaction takes place under drastic conditions with excess of hydrogen halide. In the cleavage of unsymmetrical ethers with 2 different alkyl groups, alcohol and alkyl iodide are formed depending on the alkyl groups present. Always remember, when primary or secondary alkyl groups both are present, it is the lower alkyl group that forms alkyl iodide. Let us take example of the reaction on your screen. The mechanism of this reaction is that in the first step, concentrated hydrogen iodide attacks the ether and protonated ether and iodide ion is formed. The iodide ion is a good nucleophile and attacks the least substituted carbon attached to the oxonium ion. This then leads to the formation of an alcohol molecule. Now we know that when primary or secondary alkyl groups are present, it is the lower alkyl group that forms the alkyl iodide. But when one of the alkyl groups is a tertiary alkyl group, then the halide formed is a tertiary halide. The first step for the reaction involves the attack of the proton on the ether and leads to the formation of a protonated ether. This is followed by the departure of leaving group, that is CH3OH, which creates a more stable carbocation, CH3(3)C+. Therefore, this reaction follows SN1 mechanism. The iodide ion then attacks the carbocation to form the respective alkyl halide. Another type of cleavage by hydrogen halides is of alkyl aryl ethers. They are cleaved at the alkyl oxygen bond due to the low reactivity of aryl oxygen bond. The reaction yields phenol and alkyl halide. Let's take the example of anisole to understand the reason. In case of anisole, methyl phenyl oxonium ion is formed by protonation of ether. The bond between OCH3 is weaker than the bond between OC6H5. This is because the carbon of phenyl group is sp2 hybridized and there is a partial double bond character. Therefore, the attack by halide ion, which in this case is the iodide ion, breaks OCH3 bond to form CH3I. The other types of reactions which aryl alkyl ethers undergo are electrophilic substitution reactions. The alkoxy group in ethers, which we call OR, is ortho-para-directing and activates the aromatic ring towards electrophilic substitution reactions. The first electrophilic substitution reaction is halogenation. Phenyl alkyl ethers undergo usual halogenation in the benzene ring. For example, anisole undergoes bromination with Br2 in ethanoic acid even in absence of iron 3 bromide catalyst. In this reaction, para-bromoanisole and ortho-bromoanisole are formed. The para-isomer is obtained in 90% yield. The next reaction is Friedel-Crafts reaction. Anisole undergoes Friedel-Crafts reaction with alkyl halide and acyl halide in presence of aluminium chloride, which is a Lewis acid, as catalyst. The alkyl and acyl groups are introduced as ortho and para positions. Well, that was a lot of theory. In case you feel the need for notes, do log on to www.topperlearning.com and you will get the learnings in a nutshell. It is time for a break now, but don't go away because coming up on the other side of the break is Exam Decoded.